Hello. In the last lesson we discussed Gauss's law. What does Gauss's law deal with? Do you remember the concept of Gauss's law? Gauss's law gives you a statement about the net flux either leaving or entering a surface. What does it relate to? The net flux leaving a surface is proportional to the amount of charge inside the surface. To be more specific, the net charge leaving a surface is 4 pi k times q inside, or it will be the amount of charge inside divided by epsilon naught. Now, this principle can be very conveniently used to obtain electric field due to extended charged objects. Now, you can actually avoid using calculus in many occasions. Well, we're going to look at a couple of cases where we can find the electric field due to extended charged objects using Gauss's law. Alright, let's do the first case. To begin with, we will discuss electric field at a point due to an infinite plane charge. Now, what is an infinite plane charge? Now, consider a plane charge that carries charge and it is infinite. It is extended in all directions to infinity. In other words, it simply means a very large plane charge. Now, what is the electric field at a point due to an infinite plane charge? Well, what do? There is a standard method that we use in using Gauss's law. We can use Gauss's law to find an electric field near an infinite plane charge. Alright, consider an infinite plane charge. I have drawn a section of that infinite plane charge, and the plane charge carries a surface charge density sigma. Field lines leaving the upper as well as lower surface of the plane surface will be perpendicular to the surface. There will be electric field lines leaving the top surface and also leaving the bottom surface. Is that right? Assume that the charge carried by the plane surface is positive. That means electric field lines will be originating from it. So above the surface, the field lines will be directed upward, and below the field lines will be directed downwards. Just like we have shown here. The field E has the same magnitude, so above the surface and below the surface, the magnitude of the field at any point near it will be the same, but they are oppositely directed. Is that right? Now, in order to find the field at a point, we choose a Gaussian surface which encloses a small portion of the charge carried by the plane. Now, this is the standard method of using Gauss's law. For example, let us say we want to find the electric field due to the charge carried by a plane surface like this. Now, what is the meaning of a Gaussian surface? Alright, this is my plane charge and I want to find the electric field at this point. Can you see where I'm pointing? Now, we are going to construct a Gaussian surface which contains that point. Now, the Gaussian surface in this case can be something like this. We call it a pillbox. You know what a pillbox is? Something cylindrical. So, this is the Gaussian surface. Now, that means when you put the Gaussian surface on the plane charge, inside the Gaussian surface there is a certain amount of charge. Now, how much charge is there? What is the area of this Gaussian surface? If the area is A of the Gaussian surface, then the amount of charge inside the Gaussian surface will be that A multiplied by sigma, where sigma is the charge density on the plane. Now you can see the electric field above the plane will be directed upward, and below it will be directed downward. And the point where I want to find the electric field is on this pillbox, which we call the Gaussian surface. So in order to use Gauss's law to find the electric field at a point, we take a Gaussian surface that contains the point where we want to find the electric field. And the Gaussian surface will be enclosing a part of the surface, so that we know the electric charge inside the Gaussian surface. Why do you want to know the electric charge inside the Gaussian surface? Because we are going to use Gauss's law. What does Gauss's law say? It says the net flux that leaves a surface is 4 pi k times q inside. We need to know the amount of charge inside the Gaussian surface. In my diagram, this is the Gaussian surface, which is like a pillbox. So, in order to find the field at a point, we want to find the field at a point somewhere here. So we take a Gaussian surface that contains the point where you want to find the electric field. And that Gaussian surface encloses a small portion of the charge carried by the plane. Okay. The Gaussian surface we have chosen is in the form of a box or a cylinder. You can actually take any convenient shape that you choose. Since the curved surface of the cylinder is parallel to the planes, you see, this is the curved surface of the cylinder. Like the pillbox I used was this, like cylindrical. The curved surface are parallel to the electric field lines. That means there is no flux leaving or entering the curved surface. There is flux leaving the upper surface, and there is flux leaving the lower surface. But there is no electric flux leaving the curved surface. Why? Because the curved surface is parallel to the electric field. If A is the area of the top surface of the Gaussian surface, and E is the electric field that we want to find. Suppose E is the electric field at this point, and A is the area of the top surface. Then what is the net flux leaving the top surface? The flux leaving the top surface will be E times A. I suppose this is now very familiar to you, because E, the electric field, is flux per unit area. So the total flux leaving that surface, which is actually a circle, is that right? This is a circle. That A is that area. And I want to find the electric field at a point on my pillbox over here. So the net flux leaving that surface will be E times A. Similarly, there is a similar quantity of flux leaving the lower surface. All right. Now, since the flux leaves at both faces of the cylinder, the amount of flux leaving the upper surface will be E times A, and the amount of flux leaving the lower surface is also E times A. So what is the total flux leaving the cylindrical surface? That will be 2 times E times A. And according to Gauss's law, that net flux leaving the Gaussian surface must be equal to 4 pi k times q inside. Since A is the area of the plane which we talked about, the charge inside that Gaussian surface, what is the charge inside the Gaussian surface? Which is A times sigma. Therefore, the charge inside equal to A times sigma. We are now ready to use Gauss's law. What is Gauss's law? Gauss's law is phi net equal to Q inside divided by epsilon naught, which is the same as 4 pi k times Q inside. This is more convenient, so we will use this. The net flux equal to Q inside divided by epsilon naught, and Q inside is 2EA, and phi net equal to 2EA, and Q inside is A sigma. Let's replace those. We get 2EA equal to A sigma divided by epsilon naught, and notice A and A will cancel from both sides, and what is therefore E equal to? You can solve for E. E equal to sigma over 2 epsilon naught. Well, if you remember, in the last class we used calculus to derive the same equation. The electric field very close to, this is the equation we obtained using the close point approximation for the field near a plane charge. So, or the field near, if you remember, the field at the axis of a plane charge, when you use the close point approximation, we obtain the same equation. And that we got it without calculus and without a lot of hassle. So what is the field at a point near an infinitely charged conductor? E equal to sigma over 2 epsilon naught. The field near an infinite plane charge is E equal to sigma over 2 epsilon naught. If I have an infinitely charged plane surface anywhere near, well, when we say near, a reasonable distance, is that right? Anywhere near this plane charge, the field will be sigma over 2 epsilon naught. Now that idea we will use as we go on, so that must be very clear to you. And sigma over 2 epsilon naught is the same as 2 pi k sigma. Alright, let's do a problem. An infinite plane of surface charge density sigma equal to 4.5 Newton nanocoulomb per meter squared lies in the YZ plane, and the second infinite plane of surface charge density negative 4.5 nanocoulomb per meter squared lies in the plane parallel to the YZ plane at x equal to 2 meter. Find the electric field at x equal to 1.8 meter, at x equal to 5 meter. Well, we have two plane surfaces like this, and each is in the YZ plane. In other words, it is vertical. Let's draw a diagram of that. Now, this is the first infinite plane in the YZ plane. Look at this, x-axis, y-axis, z-axis. So the vertical plane is the YZ plane. The surface charge density on this is sigma, and on the second one is negative sigma. Is that right? The surface charge density on the first plane is positive 4.5 nanocoulomb per meter squared. On the other one, it is negative 4.5 nanocoulomb per meter squared. Now the field lines start at the positive and go towards the negative. So the electric field lines between these two planes will be like this. They will start at the positive and end at the negative. Alright? In the space between the two planes, the field due to the positive plane is in the same direction as the field due to the negative plane. Why? The direction of the electric field is the direction in which a positive test charge will move. If you place a positive test charge here, it will move away from the positive and towards the negative. That means the electric field in between the two planes will be the same direction due to both these charges. The electric field due to the positive charge will be directed away from it, and the electric field due to the negative charges will be directed towards it. And that means the electric field between these two planes will be represented by parallel field lines. The field will be uniform anywhere here. You see, the electric field will have the same value at any point in between these two planes. And you can find that using Gauss's law. Now, between the two planes, these two fields add up. That means the field due to this plane will add up to the field due to the second plane. Now, what is the electric field at a point due to an infinite plane? The field near an infinite plane charge is, you remember that we just derived the equation, is sigma over 2 epsilon naught. E equal to sigma over 2 epsilon naught. So, if you take a point here, the electric field at this point due to the positive plane charge will be sigma over 2 epsilon naught. The field at that point due to the negatively charged plane also will be sigma over 2 epsilon naught, and they are both in the same direction. That means they will add up to produce a net field. The field at any point between the two plates therefore is sigma over 2 epsilon naught, that is due to the positive plate, plus sigma over 2 epsilon naught, that is due to the negatively charged plane. They are both in the same direction, therefore they add together to give you the net field at that point. What is that equal to? Sigma over epsilon naught. And now that is a very important result. Very often we will consider this. If you have two plane charges like this that are kept very close to each other, what is the electric field at any point in between? The electric field at any point in between is sigma over epsilon naught, where sigma is the charge density at either of these plates. But remember, in such a case, one is positively charged, the other is negatively charged. Otherwise, this will not be true. If two plane charges, one positively charged and the other negatively charged, are kept close to each other, then the field in between, the field at any point in between, will be given by sigma over epsilon naught. Okay, I will ask you this a little while later, and I suppose you will then remember this. Okay. Therefore, the field at x equal to 1.8. Now, what is the distance between these two planes? Well, the distance between the two planes is 2 meters, because the first plane is at the origin and the second plane is at x equal to 2 meters, and therefore we need to find the electric field at x equal to 1.8 meter. Where is that point? X equal to 1.8 is inside the two plane surfaces. That means the field at that point will be sigma over epsilon naught, and sigma is 4.5 times 10 to the negative 9, and epsilon naught, well, we have been using that value, 8.85 times 10 to the negative 12. Therefore, the field at that point is 508.5 Newton per Coulomb. In fact, you can take any point in between. The field at x equal to 1 meter will be this. The field at x equal to 0.5 meter will be this. The electric field at x equal to 1.9 meter will be this. The field at any point in between these plane charges will be this, because the field in between is uniform and is the same at all points in between the two plane charges. Okay, so we did A. How about B? Field at x equal to 5 meter. We need to find the field outside of this negative plane. Find the electric field at x equal to 5 meter. Well, to the left of the positive plate, the field due to the positive plate will be in that direction. Is that right? Now these red lines represent so the electric field on the left of the positively charged plane will be directed to the left. Now, in this region, there will be also a field produced by the negatively charged plane. What will be the direction of those field lines? You see, the field lines are directed away from a positive charge and directed towards a negative charge. That means in this region, that is to the left of the positively charged plane, the electric field due to the positive charge will be directed away from it, and the electric field due to this negative charge will be directed towards it, and that will be these green lines. That means what will be the sum of these two fields? They will cancel each other. There will be no net field outside to the left side. So to the left of the positive plate, the field due to the positive plate, that is these red field lines, is in the opposite direction as the field due to the negative plate. They cancel each other. That means there is no net field to the left of the positive plate. How about to the right of the negative plate? A similar situation exists. To the left of the negative plate, the field due to the negative plates are these green field lines, and the field due to the positive will be the red field lines. Again, they will cancel each other. The field due to the positive plate will cancel the field due to the negative. Therefore, there is no net field to the right of the negative plane. What that means is, if I have two infinitely large charged planes, one positive and the other negative, there will be no electric field to the left of this plate or to the right of the other plates. Electric field will exist only in between the two plates, and the field in between will be uniform and the same at all points. All right. And therefore, what is the field at x equal to 5? X equal to 5 is a point outside the two plane charges. Therefore, that field will be equal to 0. There will be no electric field at points to the left of the positive plane and at points to the right of the negative plane. I hope that is clear. Field due to a spherical shell of charge. Now, I've been using my basketball very often. Now, you know that if you cut this ball open, what is inside? Well, inside you have air. So this is a shell. That means it is a very thin shell. Those who have cut open a basketball will know. This is a spherical shell. What is the electric field due to this spherical shell? We're going to look at inside the shell and outside the shell. Well, you know what the electric field at the surface of the shell is. Well, you must be clear about this. Now, if you charge this shell, the electric field at any point on the surface of the shell will behave as though all the charges on the shell is concentrated at its center. And therefore, the electric field at any point on the surface of the shell will be kq over r squared, where r is the radius of the shell and q the total amount of charge the shell carries. And what will be the direction of that electric field? We talked about that in the last class. The direction of the electric field will be at right angles to every point on the surface of the shell. Alright? So, the electric field at a point on the surface of the shell will be kq over r squared. We will now use Gauss's law to find the electric field at a point inside the shell and the electric field at a point outside the shell. Alright, let's do that. What is the method in using Gauss's law? Remember, the standard method is, if you want to find the electric field at a point, we take a Gaussian surface that contains the point. Alright, that's what we're going to do. Consider a spherical shell of radius r that has a total charge q. Now, this is a spherical shell of, well, the spherical shell is the yellow colored, and it carries a charge positive q. The radius of the shell is r. You can see inside the shell it is hollow, and that's why it's called a shell. Now, by symmetry, the field due to this charge must be radial, and its magnitude depends on the distance from the center of the charge. So as you move away from the charge, now here this is the shell, and we want to find the electric field at any point outside at a distance r. And you know that as you go away from the shell, the electric field will become weaker. Is that right? And that's what this sentence means. By symmetry, the field due to the charge on this shell must be radial. What's that mean, must be radial? Radial means directed along the radius, and that's what I said, it'll be at right angles. So it will be, the field will be directed along the radius, will be radial, and depends on the distance r of the point from the center of the shell. Alright? To find the electric field E at a point, we need to find the electric field, say, at this point. What do? We construct a Gaussian surface, which is a sphere. Now, this blue sphere, or blue shell, another shell. Now, I want to find the electric field at this point due to the charge on the shell. So what do? I construct a Gaussian surface, which is a shell of radius equal to this r, because the point is at a distance r from the center of the shell. We construct a Gaussian surface which is a sphere of radius r, such that r is greater than the radius of the shell. And now we have constructed now the Gaussian surface. What do you now do? If ER is the field at the point, E sub r stands for electric field along the radius. Is that right? Along the radius, which is actually at right angles to the surface of the shell. So if ER is the field at this point, at a distance r from the spherical shell, then what is the net flux crossing the Gaussian surface? Now the Gaussian surface is a shell of radius r. What is the area of such a sphere, a spherical shell? What is the area of a sphere? Is 4 pi r squared. So if E is the electric field, means the flux per unit area is E sub r. So the net flux, the total flux crossing the Gaussian surface will be the total area, which is 4 pi r squared, multiplied by E sub r, which is flux per unit area. So the net flux crossing the Gaussian surface will be E multiplied by the area of the Gaussian surface, 4 pi r squared. Alright, now according to Gauss's law, this net flux must be equal to what? Must be equal to Q inside divided by epsilon naught. But according to Gauss's law, phi net must be equal to 4 pi k times Q inside, which is the same as Q inside divided by epsilon naught. In this case, this is more convenient because of the 4 pi in the phi net equation. Because these two are going to be equal, is that right? The net flux leaving the Gaussian surface equal to 4 pi k times Q inside. So we take these two and equate. ER times 4 pi squared equal to 4 pi k times Q inside is the amount of charge carried by the shell. And all that charge is inside the Gaussian surface. And therefore, this is the charge carried by the shell. Now, therefore, what is ER equal to? ER equal to KQ divided by R. Isn't it interesting? ER equal to KQ divided by R squared. In other words, when you charge a spherical shell, if you want to find the electric field at any point outside it, the charge on this behaves as though it is a point charge. Isn't this the point charge equation we had derived some time ago? Electric field at a point E equal to KQ over R squared. What it tells you is that the charge on the shell behaves as though all of it is concentrated at its center. Now don't confuse here, charges are not inside the shell, charges are actually outside. But the equation for the electric field suggests that the behavior is as though all that charge is concentrated at the center, so that E equal to KQ over R squared. You remember in the beginning I said, what is the electric field at the surface, at any point on the surface of the shell? The electric field at any point at the surface will be KQ over big R squared. For the surface, the distance of any point on the surface from the center will be that radius. And as you go away from the surface, as R increases, the electric field will keep on decreasing. So the maximum electric field is at the surface. As you go away from the surface, the electric field decreases. And now, this is the same as if you use K equal to 1 over 4 pi epsilon naught. It will be 1 over 4 pi epsilon naught times Q over R squared. What does it tell you? It tells you the electric field varies inversely as the square of the distance from the center of the shell. Alright. What is the field at any point inside the charged shell? Now, the equation we derived in the last slide was the electric field at any point outside the charged shell. If you now go inside the charged shell, how do you find the electric field inside the charged shell? Well, if you take a Gaussian surface inside the shell, is it possible to take a Gaussian surface inside the shell? What will be the charge inside? Is there any charge inside the shell? No, there is no charge inside the shell. Charges exist only on the shell. There is no charge inside the shell. Inside the shell it is, not empty space, but there is no material there to hold the charge. So if you go inside the shell, there is no charge inside the shell. So if you take a Gaussian surface inside the shell, there will be no charge inside that Gaussian surface. What does that mean? Since there is no charge inside the shell, there is no flux crossing the Gaussian surface. You see? You take a Gaussian surface inside the shell, there will be no flux crossing the Gaussian surface. Why? Because there is no electric charge inside there. Therefore, the field at any point inside the charged shell will be zero. There will be no electric field inside a charged shell. Can you believe that? In fact, many scientists refuse to believe this. It was Faraday, a scientist called Faraday, who first proposed this. He said if you take a shell and give it any amount of charge you want, there will be electric field on its surface, there will be electric field outside the shell, but he said there will be no electric field at any point inside. And many people refuse to believe it. Many scientists refuse to believe it. So you know what he did? He constructed a big spherical shell and went inside of it and stayed there. He put a chair in there and stayed there and started doing his work. And he asked his assistants to put large quantities of electric charge so that it began to spark outside. You couldn't go anywhere near it because it carried so much of electric charge. And Faraday was comfortably reading inside, not even knowing what was happening outside. There is no electric field inside a charged shell. Inside a charged shell is shielded from electric field. That is a beautiful result. So inside a charged shell, there is no electric field. So if you look at this, where is the electric field maximum? The electric field is maximum at the surface, at any point on the surface of the shell. That's where you got the maximum electric field. Now, inside, anywhere inside, there is no electric field. And as you go away from the surface, the electric field decreases as 1 over 4 pi epsilon naught times Q over R squared. This is the behavior of the electric field outside the shell. And at any point on the shell, the electric field will be KQ over R squared. Alright, let's do a problem. A spherical shell of radius 6 centimeter carries a uniform surface charge density sigma equal to 9 nanocoulomb per meter squared. What is the total charge on the shell? Find the electric field at r equal to 2 centimeter, at r equal to 5.9 centimeter, at r equal to 6.1 centimeter, and at r equal to 10 centimeter. Well, all we need to do is use the formulae we derived. The radius of the shell is 6 centimeter, 0.06 meter. The surface charge density is 9 nanocoulomb per meter squared. Now, area of the shell, you know, is 4 pi r squared, where r is the radius of the shell. And therefore, can you calculate the total amount of charge carried by the shell? If the radius of the shell we know is 0.06 meter, the area of the shell, the spherical area, will be 4 pi r squared, and that will be, if you know your r, we can calculate the area. The total charge on the shell will be the area multiplied by the surface charge density. Is that right? Sigma stands for charge per unit area. Multiply that with the area, you will get the total charge on the shell. So the total charge on the shell is 4 pi r squared times sigma. You know the radius, you know the value of sigma. Using that, the value of Q equal to 4.07 times 10 to the negative 10 coulombs. So now you know the amount of charge on the spherical shell. And what is the equation for the electric field at a point outside the outside the charged shell? It will be KQ over r squared. So all you need is the value of Q and the value of R. Alright, let's start with the first A. Find the electric field at, what's the first point we need to find? At R equal to 2 centimeter. That's right. Find the electric field at R equal to 2 centimeter. Tell me, where is this point? The radius of the shell is 6 centimeter. Therefore, a point R equal to 2 centimeter is inside the shell. What is the electric field inside the shell? Is 0. So, what is the electric field at a distance R equal to 2 from the center of the shell? Field at any point inside the shell is 0. Therefore, the electric field at that point is 0. How about C? What is the electric field at R equal to 5.9 centimeter? Because the radius is 6 centimeter, R equal to 5.9 centimeter is also inside that shell. And again, the electric field is 0. So, we've done A, we found the amount of charge on the shell. In B and C, both these points are inside the shell. The electric field inside the shell is 0. How about D? Electric field at R equal to 6.1 centimeter. It is outside the shell. There is a value for field there. Field at any point outside the shell will be E equal to KQ over R squared. We just calculated Q, we know it. R is 6.1 centimeter, 0.061 meter. So R equal to 6.1 centimeter, which is 0.061 meter. KQ, Q we calculated as 4.07 times 10 to the negative 10 coulombs. and R is 0.061 meter. The electric field is 984.4 Newton per coulomb. And how about the electric field at R equal to 10 centimeter? Well, that again is an outside point. What all we need to do is replace your R by 0.1. So at R equal to 10 centimeter, electric field is KQ over R squared, where R is 0.1 meter, that is 366.3 Newton per coulomb. Alright, let's look at another problem. A spherical shell of radius R1 carries a total charge Q1 that is uniformly distributed on its surface. A second larger spherical shell of radius R2 that is concentric with the first. So you got a first spherical shell of radius R1 and a second spherical shell, a bigger one, which is concentric, means both have the same center. So the first shell is inside the second shell. Now that is distributed uniformly over its surface. Use Gauss's law to find the electric field in the regions where R is less than R1. What does that mean? R is less than R1. R1 is the radius of the first shell. R is less than R1 is inside the first shell. Now R1 less than R less than R2. You see, you have an inner shell and an outer shell. So R1 less than R less than R2 is any point in between the inner shell and the outer shell. And then find the electric field at points corresponding to R greater than R2, that is outside of both shells. What should be the ratio of the charges Q1 by Q2 and their relative signs for the electric field to be 0 for R greater than R2? If you want the electric field to be 0 outside the system, what must be the ratio of the two charges and what must be their signs? And finally, sketch the electric field lines for the situation in B when Q1 is positive. Well, you know how important it is to get a mental picture of a problem. Always read a problem a couple of times and form a mental picture. Alright, now here I have the inner shell and the outer shell. The radius of the inner shell is R1 and the radius, and it carries an amount of charge Q1 that is uniformly distributed on it. The radius of the outer shell is R2. Well, I think my line went a little overshot. It must stop here. So the radius of the outer shell is R2 and it carries an amount of charge Q2. Okay, what is the first thing that we need to find? Use Gauss's law to find the electric field at a point such that R is less than R1. You see, the small r is the distance of the point you want to find the electric field from the center. If R is less than R1, it means it is a point inside the inner shell. Now, what is the electric field inside that inner shell? The field at any point inside the shell is 0. Therefore, the electric field at a point R less than R1 is 0. The electric field at a point inside that inner shell is 0. Now we want to find the electric field at any point between the inner shell and the outer shell, somewhere here. R1 less than R less than R2. Now, how do you find the electric field there? Well, if you take a point here, that point is inside the outer shell. That means the electric field due to the charge on the outer shell will be 0 there, and it is outside the inner shell. I hope you follow my argument. If you take a point here, it will be inside the outer shell and outside the inner shell. That means the field at that point will be purely due to the charge on the inner shell. Alright, let's write that down. For a point in between the inner and outer shell, these points are inside the bigger shell and outside the small shell. Now, the bigger shell will not contribute to the electric field because the electric field inside the shell is 0. But the inner shell will contribute. The field at points in this region, in the region between the two shells, is purely due to the charge carried by the inner shell, which is Q1, the charge on the inner shell. And what is the mathematical expression for that field? The field at any point in between the shell will be purely due to this Q1, which will be KQ1 over R squared. That will be E equal to KQ1 over R squared. That is the expression for electric field at any point in between the two shells. Alright, how about the next one? For R greater than R2. See, R greater than R2 means a point outside of both the shells. And the field outside of both the shells will be due to the charge on the outer shell as well as the charge on the inner shell. It will be due to Q1 plus Q2. So that will be E equal to K, the total charge will be Q1 plus Q2 over R squared. At any point outside of the two shells, the electric field will be K times the total charge on the two shells divided by R squared. And B, for the electric field to be 0. Now we have been told to find the ratio of the two charges which will result in the electric field outside to be 0. Now when will this become 0? This is a rational expression. This is the electric field outside the two shells. And in B part, we have been told to find the ratio of Q1 to Q2 that will result in the field at any point outside to be 0. Now tell me, when will this quantity become 0? This rational expression becomes 0 only when Q1 plus Q2 becomes 0. If Q1 plus Q2 equal to 0, it means Q1 equal to negative of Q2. You see, this is the only way the electric field at any point outside the system can become 0. So if the electric field outside is 0, it means Q2 equal to Q1 or Q1, well, Q2 equal to negative Q1 or Q1 equal to negative Q2. That means Q1 divided by Q2 will be negative 1. So, if the field outside the system is 0, it means if the charge carried by the inner shell is positive, then the charge carried by the outer shell must be equal in magnitude but opposite in direction. And that is the answer for this. The ratio will be Q1 over Q2 equal to -1, and they must be equal and opposite. And how will the field lines look? If the inside is positively charged, the field lines will start from the positive charge and end in the negative charge. So the electric field lines will originate at the inner shell and terminate at the outer shell, in the space between them. The field lines will look like this. Q1 is the charge on the inner shell, Q2 is the charge on the outer shell, and the electric field will be represented like this. I suppose we finished talking about that problem. Now what I'm going to do is I'm going to stop this part of the lesson here. I will record a second part of this lesson, for which I will see you in a little while.